So the first thing you need to know about me is that I'm not Graham Cohen. I did not write BitTorrent. I'm not the founder and CEO of Chia Network. I am the co-founder and former COO, CFO of Storage Labs. I've been working in distributed storage for the last several years. I am a watch collector, ethical software activist, and curry enthusiast. I'm here to talk about Chia Script and all of the terrible things that we're going to do to Bitcoin D as part of this. I've been working with Chia for the last couple months as kind of an engineer and consultant around Bitcoin D and all of these various ways it can really trip you up. So Bram wanted to talk about proofs of space and time, so I'm going to take questions on that at the end if you don't mind. I'm not prepared to give the full pitch because I think right now Bram is the only person in the world who can do that. We're working on the knowledge transfer thing. All right, so how many of you have worked with Bitcoin Script? All right, like 3-4 people. Bitcoin actually supports a very minimal Forth-like stack-based language in its transactions. Frankly, it kind of sucks. It's really terrible. If you've used Forth, you'll know that. It's weird. So, for example, Script has the concept of -0. Yeah, it has -0. It's different from normal 0. All the arithmetic is the same, but if you hash 0 and hash -0, you're going to get different things. All right. So here's another way that Script is really weird. You have these two operations called bool and bool or. You'd expect these to be Boolean and Boolean or. They're not. They check whether the inputs are empty strings and return a Boolean. So it makes no sense. It's frankly terrible. So Script is hard to upgrade. We're stuck with whatever Satoshi gave us. In the past, there have been two major upgrades, opcltv and opcsb, which both relate to time locks. And for backwards compatibility reasons, they both have to pretend to be opnops. So that if there's an old client who doesn't understand check lock time verify or check sequence verify, it has to pretend it's a no operation. So for that reason, we have things like this, where you put in the time that you want to lock it for, op check lock time verify, and then op drop. Because check lock time verify reads the stack, but does not pop the argument from the stack. So we need to then drop it from the stack after CLTV has read it. Check sequence verify works the same way, and it's really kind of a pain, and it means that you never see CLTV without op drop immediately afterwards. So one extra useless byte just because we have to maintain backwards compatibility with Satoshi's original script, which is annoying. Script is really messy. So for example, opif, you think it's a conditional, but it's not. Opif is actually control logic that mutates the stack based on what path the user wants to execute. So oppick is supposed to take things, copy a stack item to the top of the stack, but it mutates the stack before it does that. It pops a number from the stack and then reads that number down and copies that item to the top of the stack. So oppick is abjectly terrible. You have to immediately push a number and then pop that number with oppick. It's just not good. And then you have endif. Endif is not, strictly speaking, the end of the if block. Endif is an actual operation that gets executed and fails your script if it's not after an if somewhere else. You'd think it's just for control flow, but it's an actual operation that happens and changes things. It's terrible. So Blockstream has been working on simplicity. It's going to fix everything in 2025. Like, we'll have this beautiful new world where scripts are amazing, easy to write, and it's going to come out in 5 more years. So maybe. How do you fix this? Like, what do we actually do to improve on-chain scripting? Well, we're going to make Chia Script, and it's going to be better. Chia Script is clear. So for example, no more -0. We're going to operate on bools, not strings. We're going to not have integer overflows. One of the other weird things about Script is that arithmetic supports 4-byte numbers, but can result in 5-byte numbers being put on the stack. So if you accidentally overflow in your arithmetic, your future arithmetic operations will error out. Anyway, so no more integer overflows, no more -0, none of that weirdness. Chia Script is versatile. We're going to support more things in better ways. So we're going to change the op-if semantics, we're going to have better stack management opcodes, no more op-pick, and we're going to use an upgraded signature scheme. So we're completely dropping opchecksig, opcheck-multisig, and the verify versions of those. So Chia Script's also designed to be upgradable. We're introducing a concept called abort succeed. In Bitcoin, if you run into an opcode that you don't know, it's pretty much always a NOP, and so you do nothing. In Chia Script, if you run into an opcode that you don't know how to handle, it's going to end script execution and return success. This means that all clients that don't know how to handle an opcode will just punt on it. They won't care. And so in the future, we can replace those opcodes with things that limit behavior in meaningful ways, like we did with opcheck locktime verify in Bitcoin, but we don't need to pair it with an op drop. It means that every unknown opcode, we can just socket in any functionality that we want to with no worries. And new clients who understand it will enforce that behavior, while old clients won't. It's the exact situation we have in Bitcoin, but with better semantics at every point. Oh yeah, and we're also going to reclaim most opcodes. So where do we start? Delete everything. Data pushes, Bitcoin uses bytes or opcodes 1 through 75 for just pushing data on the stack, and then it has 3 additional opcodes for pushing that. Push data 1 reads the next 1 byte and reads that as the number of bytes following that to push onto the stack. We're just going to delete all of those and standardize on push data. Push data is going to read the next bytes as a variable length integer and push that many bytes onto the stack from the string. So we're no longer using just 78 opcodes straight up just for pushing data. We now have 1. You don't have to memorize what 1 through 75 is in hex anymore to read Bitcoin scripts. We're just going to have like 1 opcode that handles all that for you. Stack management, let's see. So Bitcoin actually has 2 stacks in its script, which is a terrible idea. You actually like push things onto the alt stack and pop them off and move them back and forth from the normal stack to the alt stack, and it's really a mess, and nobody uses this feature because, you know, frankly, you can't effectively. Humans don't think that way. All the rest of these are for manipulating items on the stack. So like, for example, op2 rot takes the first and stack item and moves them to the 5th and 6th position and moves everything else up. It's really kind of pointless, and so we're going to get rid of all of these. You can keep op-depth. Like, op-depth is pretty fine. It reads the stack and pushes a number onto the stack that is how many arguments are below it. So if there are 3 items on the stack, it's going to push a 3rd. It's actually kind of useful. Op-drop is pretty useful too. We want that to keep that, but, you know, out of all of these, something like 20 opcodes, we're going to keep about 2. And all of these crypto operations, we're just going to get rid of them, and you get to keep SHA-256. That is the only one of those things you should actually be using. I mean, look, we've got SHA-1, RMD-160, and then we have Satoshi's just like weird composed hash functions that don't actually add any benefit. RMD-160 of SHA-256 is not a thing that people should do. That's just Satoshi being weird. Opcode separator is maybe the worst thing anyone ever added to Bitcoin. It just causes complications with everything, and there's entire swaths of the code base that deal with it, like hundreds of lines of the Bitcoin D code base deal with it, and we're just going to delete them because they're a pain in the ass. Excuse me. I have strong feelings about this. All right, so you get to keep SHA-256 because that's a reasonable hash function that people want to use. Why do you remove opchecksig? Because we're actually removing ECDSA altogether.
What?
I'll get to that in a second.
Is it quantum computer dependent?
We don't know that, though. All right, so double SHA is pointless, RMD-160 is pointless, hash-160 is just like a mess. We're just going to trash all of that, and you can use a real hash function that people actually use. So what about signatures? Here we go, Tarek. We'll get there. So the next thing we do is make things better. We're going to go with Mast first. Mast is an upgrade for Bitcoin scripting language where we take our scripts and build them into Merkle trees. And then we selectively reveal the parts we want to execute. So what this means is that scripts take up less space on chain. You don't end up with all the op-if, op-end-if messy semantics. You reveal the parts of the script that you want to execute and provide a proof that that is a valid route through the script. So we're going to go Mast first. And it's just, it's a no-brainer. It's a strict upgrade. It improves privacy, scalability, everything. I would highly recommend, if you haven't already, go read the BIPs for tail call semantics and Merkle branch verify. We're going to end up with something similar to that. All right, so we're going to improve all of the opcodes that we're keeping and a bunch of them that we're not. So we're going to I talked about abort success earlier. We're going to have an opcode that will always be abort succeed. So you can always just return a script on a success at any point in the script if you want to. So it does what it says on the tin. It stops script execution, it returns success, and this is the default behavior for unknown opcodes so that we can upgrade them in the future. So we're adding opcltd drop and opcsv drop. They do exactly what they say. It's check lock time verify and drop as one opcode. The way we would have liked to do it in Bitcoin if we weren't stuck with op-nopping it. It behaves as check lock time verify or check sequence verify. It pops a stack item instead of just reading a stack item and fixes the annoying op-nop, op-drop thing. All right, to replace pick and all of these stack management, we're going to add two new opcodes, which are pull and deref. So these are new ways to read the stack and copy it to the top. So they're going to copy the stack item at a specified index. So every time you pick or deref, the following bytes will be a variable length integer telling you which stack item to copy to the top. Pick indexes from the top of the stack and deref from the bottom of the stack. One of the things you might have noticed about op-pull is it becomes extremely difficult when you're referencing from the top of the stack to determine where something is over time. When you're mutating the stack and you want to read the second from the top item, if you keep pushing things, it's going to move down to the 5th position, and you have to remember where it is. However, when you're reading from the bottom of the stack, it stays at a set index. So opderef makes it way easier to reference things that are on the stack and copy them to the top. So when we're doing stack management, opderef and oppull are far better tools than anything Bitcoin gave you. All right, so here's an example. If we have this stack set up on our left, we have the script on our right. We're going to pull the item at index 2. So we're going to count from the top of the stack down to this 48-byte pub key, and we're going to copy it to the top of the stack. Then we have deref at 1, so we're going to count from the bottom of the stack, the first item, and pull it to and copy it to the top of the stack. It's just an easier, better way of doing all of Bitcoin stack management. All right, so I talked earlier about op-if being terrible and everything about it being bad. We're replacing it with if-jump, if-njump, and jump. So these are new flow controls. And what they're going to do is they're going to jump a specific number of bytes. So if the top stack item is truthy or evaluates to true, it's going to jump. If not jump is if the top stack item does not evaluate to true, it's going to jump. And op-jump just jumps if you want to do that for some reason. So these are going to replace op-if, op-else, op-endif, everything like that. So here's an example. So we're going to say op-if-jump 33. Here we go. And so 33 in hex is 51 in decimal. And so we're going to jump over this OX30 byte pub key and these 3 opcodes. So if this top stack item is true, we're going to jump to here. If the top stack item is not true, we're going to execute this, and then we're going to see this jump and jump over this statement to whatever's after it. basically what this does is all the same flow control, except it's immediately obvious where script execution will resume after the jump. You just count forward that many bytes. You don't have to parse an entire Bitcoin script ahead of time in order to see what if branches you're going to execute. You can quickly, from the length of the script, verify how much computation it's going to take to execute by counting SIGOPs and things like that. Opif is responsible for a lot of the complexity of writing and evaluating Bitcoin scripts, and jumping is going to solve a lot of that. So in this case, if the top stack item is true, we're going to check this pub key against the aggregate signature. If the top stack item is false, we're going to check this pub key against the aggregate signature. So this is a way of doing, in Bitcoin, this would be like op-if, pub key, op-check sig verify, op-else, pub key, op-check sig verify, op-end-if. So we're doing this in fewer opcodes in a way that's more clear for static analysis. So I skipped over this, op-BLS aggregate. So this is tying back to the signature schemes we talked about or didn't earlier. So what is op-BLS aggregate and op-BLS aggregate from stack? Chia is going to use a completely different signature scheme called BLS Signatures. These have also been called BLS short sigs. They're based not on elliptic curve cryptography, but on pairings-based cryptography. And I'm going to go through that in a second for anyone who likes math. So what we need to know right now is that op-BLS aggregate is going to read a pub key from the stack, compute the pairing of the pub key and the message, which I'll get to in a second, and adds it to the aggregation verification queue. One of the great things about BLS signatures is that they can be non-interactively aggregated. You can take any number of BLS signatures and transmit them in the space of one BLS signature. You can just linearly squish these all down into one signature on any number of messages and pub key pairs. And so when we're talking about Chia versus Bitcoin, in Bitcoin, every transaction has a, I think, 65-byte ECDSA pub key per input, at least one, potentially many. And then each one has a 33-byte signature. No, sorry, those are backwards. 33-byte pub keys, 65-byte signatures in ECDSA. In Chia, every transaction has exactly one aggregated signature. So you take all of those signatures that are taking up a lot of space in the blockchain, squish them down into one thing. And if we extend SegWit a little bit, we can actually have those just hanging off the blockchain, taking up basically no block space ever. So it's kind of a no-brainer to do this for us. Op-BLS aggregate from stack implements the logic that people want with check sig from a stack in Bitcoin. It reads a message and a pub key off the stack, computes the pairing, and adds it to the verification queue. This may not make sense yet. Just don't worry about it. We'll get there. So what are next steps for Chia Script? We're going to be writing, this is one of Bram's pet projects, a Bitcoin to Chia transpiler. So take any Bitcoin script that you have, transpile it to Chia Script. All you have to do is swap out the key formats. So for example, we're going to take, this is the exact thing I had on the board earlier. We're talking about op-if, pub key, check sig verify, else pub key, check multi-sig verify. We can do that in Chia Script with jumps. So this is going to be the exact same semantics, but it's more compact, more concise, and we're going to just transpile your old scripts so that if you like writing in Bitcoin script, you can. So we're going to build some tooling around masks. I talked about this earlier, but we need some nice command line or debugging tools to Merkleize a script, select portions for executions, verify the proofs, provide the inputs to the script, execute it, and debug from command line. This is something that still barely exists in Bitcoin. There's only 2 debuggers that I know of for Bitcoin script, and they're both kind of terrible.
Buggy.
Yeah, buggy. nobody gets the bool and thing right, and so the debuggers don't match the actual Bitcoin D implementation. But frankly, like, who would get the bool and thing right? There's absolutely no reason you would read for null strings. It makes no sense. All right. Before I dive into BLS, do we have questions about Chia Script?
Whoa!
Yeah, info
Okay,
dump.
hold on a second. Are you guys writing this stuff out for people to read?
We have internal write-ups, and we're going to be formalizing those and putting them out there. I've been authoring the chips so far.
Yep.
So we're going to...
When is the release date for the first drafts of these things?
That's a tough question. Always 2 months later than we expect. So one of my roles with Chia has been writing these things down while we talk about them, and I'm hoping to get those out to the public within a month or two, but we'll see what happens.
How do you guys vote on BLS versus
ECDSA?
Yeah.
So none of us like ECDSA, so that was easy. The real choice for us was BLS for Schnorr. And BLS is simpler, easier to reason about, has the advantage of non-interactive aggregation instead of interactive aggregation. So we can aggregate signatures after the fact instead of forcing users to do it. And BLS gives the shortest signatures of any signature scheme for the security parameter. So for us, it was kind of an easy decision. We explored doing Schnorr and decided it was just a bunch of headaches.
So,
Yeah.
one thing I like to do when I see code that causes me to throw things against the wall is try to understand why it was written that way.
Yeah.
So you listed a bunch of things that you want to throw out.
Yep.
Is it just like good intentions gone awry? Or is there just like fundamental issues with how these comps are?
A bit of both, really. So one of the things I didn't talk about is Bitcoin Script has a lot of disabled opcodes. So there's an opcode that's opcat, so it'll take the top 2 stack items, treat them as strings, and concatenate them. It's been disabled for years because Satoshi didn't think it through, and you can just DDoS all other nodes by doing opdupe, opcat, opdupe, opcat 10 times. You'll fill up all of their memory with just the stack for your Bitcoin script. So there's a bunch of stuff that we're left with because Satoshi did not think it through. He didn't consider the implications of these opcodes, or he didn't consider like good type checking, which is why bool and bool or happened. So a lot of this is probably he didn't think that this was as important a part of the system as other things. If you actually go look up the list of opcodes, you'll find that about probably 20 to 30% of them are disabled and will never be re-enabled. Yes?
Sorry, forgive the ignorance, but this is going to be on a different chain or on
This will be on a brand new chain.
Who's your ICO?
No, it's not my department. So this will be on a brand new chain called Chia Network. It's going to be based on proofs of space and proofs of time, rather than proof of work.
And how do you prove space?
Very carefully. we can cover that at the end.
What's the space for?
We'll cover it at the end, man.
Cover it at the end. Yes.
It's probably a dumb question, but if it's going to be on its own chain, why does it need to be? Why are you building a Bitcoin transpiler?
So that people with existing scripts can move them over easily. So for example, there's a lot of useful scripting being done around like HTLCs, Lightning Network. If we have a transpiler, we can just move all of that over immediately rather than rewriting it from scratch. Yes?
Have you guys thought about balancing, like, should we change the scripting, or should we change the proof, or should we do it all at one go? Like, are you throwing everything in the core kitchen sink into this?
So we see this as doing the low-hanging fruit. With the exception of proof of space and proof of time, most of the changes we're making are things that Bitcoin D, Bitcoin Core would do if they were starting fresh. We're not doing like something far out there like simplicity for the scripting language. We're keeping most of the script implementation, the parsing implementation, all of that. We're just changing the opcodes to be better. We're not throwing out like the idea of blocks. We're just kind of changing transaction formats and signatures to be better. We're trying not to kitchen sink it, but there may be a little bit of kitchen sink thrown in there towards the end, depending on how far we get. So, yeah.
When you guys think about, you talk about space and saving space in transactions and chain, do you have a comparison idea of like using their approach, how much space you guys would save versus, current Bitcoin implementations?
So I'll talk about that a bit more in a second, but using our aggregate signatures, if you have 2 inputs in a transaction, you're going to save something like 5 bytes per transaction. It scales linearly up from there. So you're saving like 50-something bytes after, for every additional signature, because you aggregate all of them to one signature. In terms of the script, you're not going to shave off much, maybe a few bytes here and there. We're going to have SegWit mandatory, and so we get the kind of on-chain but off-chain vbyte thing there, so probably we save a bunch of space that way as well. Any other questions? Yes?
So what's the point of SegWit from scratch? If you're starting from scratch, why do you need SegWit? Well, SegWit was just a way to extend without going to the maximum block size.
SegWit wasn't just a way to extend the maximum block size. SegWit is because Satoshi had never done this before, and he made a mistake that I think probably everyone would have made if they had never done this before. There's 2 things that are important to a blockchain. The first thing is the state changes. So what inputs are consumed, what outputs are created. The second thing is the validating information for those state changes. What gives you the right to consume those inputs and create those outputs? And in, like Bitcoin from Satoshi onward, all of that information was mixed up together. And what SegWit does is it takes the state changes and the permissions to make those state changes and breaks them apart. And once you've broken them apart, you remove problems like malleability, and you can conceptually separate what the state of the chain is from the entire history of validating the permissions on the chain. And that means that we can take the permissions and put them off somewhere else that isn't on the main blockchain, and we can reduce what goes on the main blockchain to just the state changes that people care about. It's that there is a conceptual separation there that Satoshi did not see, and SegWit kind of brings it in line with there's state changes and there's permissions, and we need those separate, otherwise everything gets really messy. Does that make sense?
Yeah.
Yes.
Is this shift to Chia Script? I know it might be a little too soon, but like you think it still support simplicity when it comes in?
I probably. There's going to be some differences because of things like the signature algorithm. We'll see exactly what happens in a few years. I'm not joking. Simplicity is going to be years out at this point. I like simplicity. Anyone who likes Haskell will like simplicity, but it's years out. All right. I'm gonna, yes.
Apologies if we've already covered that, but is there going to be a cost mechanism for the script?
No. So one of the design goals of Bitcoin Script and Chia Script is that they're amenable to static analysis, so that you can tell how many resources it will consume before you run it. In Bitcoin Script and in Chia Script, you can do this very easily by counting the number of signature operations that you're going to execute. And because you know that, we can keep it very bounded, and you don't need a cost because we can make sure that we don't run scripts that are too expensive. Or in most cases, you can't write scripts that are too expensive. I'm gonna move on to BLS. This might get a little math heavy for a bit, so I hope everyone is
Already
comfortable.
strapped in.
All right, so BLS is a signature scheme named after the three mathematicians who came up with it about 10 years ago. It's Dan Bonnet, I forgot Lynn's name. Bonnet, Lynn, Shakem. BLS is based on pairings, and I'm gonna cover a bit of like theory background here for a second. In computer science, we have a few fundamental information problems. So for example, the computational Diffie-Hellman problem. So in a cyclic group, like all the integers modulo a large prime number, if you know g to the x, can you compute x? And in basically every cyclic group that we work with, we assume computational Diffie-Hellman is very hard. We assume that it reduces to something called the discrete logarithm problem, which we assume is very hard. So there's a number of statements of this. This is one of the formalizations, is if you know g to the x and g to the y, can you compute g to the xy? And the answer is no, basically never. There's a variation of this called the decisional Diffie-Hellman. If you know in a cyclic group g to the x and h to the y, some other number, can you decide whether x and y are the same? Can you tell if two numbers have been raised to the same exponent? And usually the answer is no, you can't do that. BLS uses something called the co-decisional Diffie-Hellman problem. So with two cyclic groups, if you know a to the x, b, and b to the y, where a is in this group and b is in that group, can you tell if x is equal to y? And so BLS uses something called a pairing to make the computational Diffie-Hellman problem hard in both groups, the decisional problem hard in both groups, but the co-decisional problem easy. And so then, what we can do, ECVSA Schnorr relies on computational Diffie-Hellman being hard in elliptic curve groups. There we go, caught up to myself. All right, so what we can do is we can define a special function called a bilinear mapping. The bilinear mapping is a function, and you don't have to worry about what it does. I have no idea what it does. All it does for practical purposes is create a special function that has this incredibly special property, where you have a to the x and b to the y is equal to a and b to the y to the x. So this takes an element from the first group, an element from the second group, maps them into a third group that lives off over there somewhere. And this function has the special property that moving around exponents doesn't matter. It doesn't change the result. And don't worry about how that works. It's some kind of magic math with embedded elliptic curves and extension towers that maybe I'll understand someday. But the upshot here is that we can move exponents around, it doesn't matter, and that means that we can create a really nice signature scheme where we can determine whether two exponents are the same. So here's the BLS signature scheme. We're going to create a random private key that's an element of integers mod some large prime p. We use B12381, which uses a 381-bit prime for p. Actually, 256-bit prime for p, actually. So x is some 256-bit number, doesn't matter what, it's a secret. And then we're going to take the generator point, which is just some random point on curve 2 that we agree on altogether, and we raise it to the power of our private key. And that's our public key. Our public key is a point on curve 2. Our private key is a number. So we're going to, when we want to sign a message, we're going to hash it and map it to a point on the curve. So this is some hash function like SHA-256. Don't use RMD160, it's just a bad idea. Don't use hash 256 or Satoshi's whatever. We're going to take that hash and we're going to translate it into a point on the first curve. So our pub key is on the second curve, our message is a point on the first curve, and then to compute the signature, we're going to take the hash of our message and raise it to the power of our private key. So then for verification, we check that the pairing of our signature and the generator point on curve 2 is equal to the pairing of the hashed message and our pub key, or the other person's pub key. So here's verification broken down a bit. We've said already that we can move exponents around in the pairing, it doesn't matter. So we say that, we're pairing our signature with the generator point, and we're pairing the message with our pub key. We already said that the signature is just the message to the power of our private key. And our pub key is the generator point to the power of our private key. So we're checking whether the hash to x and G2 is equal to the hash and G2 to the x. So we're just checking that this relationship holds. And we know from earlier when we defined our mapping that that relationship should hold if those two x's are the same and should not hold if they are different numbers. So what that means is we can efficiently check whether two exponents are the same without computing the exponent. So my private key stays private, my public key is public, and you can use my public key to verify my signature on any message. All right, before we move on, do you have any more questions? Any clarification I can go with here? This is actually some of the simpler algebra that I've worked on recently. So I'm sorry if I'm moving a bit quickly. Yes?
How long has it been around and how confident are you guys that there's no?
So this has been around for almost 10 years. It's provably secure with one additional assumption. And basically what that means is Peter Woolley will raise some concerns about the one additional assumption, but other than that, it's totally fine. Nobody else cares. So it's been around for a number of years. The problem that we're going to run into is hardened implementations. So the reason everybody uses ECDSA is that the implementations have been around, constantly developed, and all of the bugs have been fixed over the last 20 years. Schnorr has been developed over the last 5 to 10 years, and this has only been implemented over the last 4 or 5 years. So it's not about the security assumptions of the scheme, it's about the implementations and how hard we can make one in the time we have. Was there another question over?
Pretty much the same. How well tested is it?
Yeah. So we're actually using the same curve that Zcash is using for their new powers of tau and the new snark setup. So the Zcash curve is going to be getting a lot of attention, and we're probably going to be moving to that one at some point in the future. Or the Zcash implementation is going to be very well tested, and we'll probably end up moving to that implementation and standardizing around it and pouring resources into verifying it.
So there's two curves to decide, right? You're using the same two curves?
Well, there's actually, you basically get a choice of paired curves. So there's two curves, but you only get one choice if you choose a pair. Yeah. You don't get to choose just any two curves. We have to choose two very special curves that you can build this special mapping for. So in terms of security level, we're using 12381, which has 128 bits of security, give or take. ECDSA signatures have about 100 bits of security right now, maybe a little less. All right, so I'm going to move on to signature aggregation. This is the neat trick I mentioned earlier, where we can take any number of signatures from other people and roll them all up into one signature. very, very easily. So this is all the same. We're just going to say that now we have n participants, and this is private key 0, private key 1, etc., etc. So we're going to generate pub keys the same way. We're going to hash things the exact same way. We're going to sign them the same way. And then we're going to aggregate them just by multiplying the signatures together. It's really easy. You just multiply the curve points. So you're just taking all of these points on G1 and multiplying them together. You get a single point at the end. And the way we're going to verify is we're going to check that the product, so this is pi down here, of the aggregated signatures, and G2, is equal to the product of all of the pairings of messages and pub keys. So the pairing of message 1 and pub key 1, the pairing of message 2 and pub key 2, all multiplied together. So we're going to, all right, so breaking it down a little bit, we're going to check that the mapping of signature 1 and signature 2 multiplied together with G2 is equal to the product of the mapping of hash 1 and pub key 1 and the mapping of hash 2 and pub key 2. So this is the same relationship we saw earlier, where we're just moving the exponents around to verify. If you want to go through and do more algebra to check that, go be my guest. We're basically just moving these outside the parentheses. So BLS has a few limitations. Actually, any questions on aggregated signatures? Yeah?
Are you talking about aggregating signatures per transaction or for the entire?
That's an implementation question. So BLS aggregate, which I talked about earlier, what it's going to do is it's going to compute this mapping and cache it, and then verify the signature when it does that, which should be super easy. But essentially, it's going to add these to a cache so that we could aggregate across an entire transaction or across an entire block pretty easily. All you need is the cached mappings and the aggregated signature for that level. We're kind of seeing this as across transactions right now until we get a better model for blocks. But we'll kind of see where that ends up. The space savings of having exactly one signature per block is pretty big, but there's limitations around once you've aggregated, you can't unaggregate. So if you want to verify the signature on a particular message, you're going to need to transmit the entire block and the entire block's aggregated signature, instead of just the single transaction you care about.
So
yeah.
That seems to imply that you can't necessarily incrementally aggregate to say that you're at this signature, we want to add one more.
You can incrementally aggregate. So think about multiplying numbers. 1 times 2 times 3 times 5 is the same as 1 times 2 times 3 times 5. But it's hard to go backwards. And this goes back to elliptic curve math and the pairing operation and stuff. Is one of the reasons we say that computational Diffie-Hellman is hard in these groups is because it's very hard to divide numbers in these groups. It is computationally cheaper to multiply than to divide by a pretty wide margin.
Okay. So that also continues to say that you can have the incremental kind of check can be done fast, and then you can also have a harder check that's done.
Right.
This entire chain we can now do more.
Yes, yeah. So you can cache all those pairings, you can verify chunks of them against an aggregated signature, you could verify all of them, you could, as long as you're caching the signatures that you see and caching the pairings on the other side, you can verify any chunk of signatures against any chunk of message pub key pairings. This gets into implementation stuff around when do you cache those, how long do you keep them, how do you communicate these to other nodes who haven't seen the entire block, that kind of thing. Yes.
So the assumption here is that a miner creating a block with 1,000 transactions is going to aggregate all the signatures for all 1,000 transactions into a single signature for the block?
Potentially, yeah. Right now, we're probably going to start by implementing transaction level aggregations. but they're non-interactive, so I could batch up 5 transactions as a unit, aggregate 5 signatures into one signature for those 5 transactions, move those around as a chunk. We can go anywhere from 1 signature to 1 message to 1 signature for the entire block. And you can aggregate up, but it's hard to deaggregate. And I don't think you can deaggregate securely. Anyways, so problems. More assumptions, fewer implementations, we already talked about this. Pub keys in BLS are 96 bytes. I mentioned earlier that ECDSA signatures are 65 bytes and ECDSA pub keys are 33 bytes. You might notice that 33 plus 65 is just barely more than 96. So when we're aggregating signatures in our script, back in script land, we had the pub keys on the stack, and then we're running opBLS aggregate on them. So what that means is if we do it that way, we're not actually saving space until we aggregate 24 signatures, and then you break even. And that's kind of problematic because not many transactions have 24 inputs or 24 signatures on them. So pub keys are revealed on chain. This is the same as ECDSA, but it leads to that problem where if pub keys are revealed on chain and the pub key is only 2 bytes smaller than ECDSA's signature plus pub key, like we don't actually get savings. So we came up with a solution, reverse BLS. It's identical to regular BLS, except the message is on curve 2 and the pub key is on curve 1. So what that means is we're doing all the same math, except we're swapping what curves things are on. So the signature is on G2 and the pub key is on curve 1, right? I hope you all at least have decided not to understand this by now, because it's the exact same stuff we went over with a slight flip. So verification's exactly the same. We're going to compute the mapping of pub key and message and the mapping of generator point and signature and verify that they're equal. So now pub keys are 48 bytes and signatures are 96 bytes. So that looks much better. So now we need just 1 signature per TX, or potentially in the future, 1 96-byte signature per block. That seems like a pretty nice space savings. It starts at 2 inputs, or you get significant space savings over any multi-sig setup. Because ECDSA multi-sig, you have to push every pub key to the stack, and it's a pain. So by using reverse BLS, we overcome the main limitation of BLS, which is the long pub keys. And before anyone asks, yes, we checked this by the authors of the BLS paper. Yes, we're allowed to do this. No, it won't break the security. All right, so that's the end of my slides.
How long have you been working on this new script architecture?
On the new script?
Well, I mean, yes, this is a lot.
Not too long. Couple weeks. I mean, all the script stuff is super low-hanging fruit. It's, all no-brainers. Script is a mess and everybody knows it, which is why we want to move to simplicity. We've been checking a lot of our changes or proposed changes by Bitcoin Core developers or other people who've worked on Bitcoin D. We're trying to make the things that are really obvious. Yes?
Is there any library using BLS? Are you going to use it or implement your own?
So there are implementations of the pairing math and the operations on the different groups. So we essentially have to build a implementation of BLS using the underlying algebra. So pairing is implemented, the scalar multiplication and the point multiplication are implemented. We just now have to go out and put all the plumbing in place. Yes?
Thank you, this is super cool. Can you share a little bit about the roadmap for the Chia project?
It's really up in the air right now, and mostly depends on what Graham feels like working on at the time. We're still in a lot of the design phase. We're working on an implementation of reverse BLS that's progressing nicely. We're mostly in design phase for script changes, for proof of work changes, for everything else.
Does that mean you're looking for engineers?
I believe they are. I'm not my department. So, yeah.
You want to give us a little bit about space and time?
Sure. I don't have any slides for this. So I guess the...
Or you have the B-paste slides on your screen?
I do have the B-paste slides around here somewhere, I think. But I don't find them very helpful, is the problem. Bram and I do not
Did you spot that?
Bram and I do not build slides the same way. Let's see if we can actually get anything useful out of here.
You have a point.
Alright. See, like, this just doesn't help anybody.
That's all Bram right there.
Okay. Let's see. Function inversion for proof of space. Alright. I think this is probably the most relevant thing. So essentially the way the proof of space works is we're trying to invert a function, and we're just going to not worry about what that function is exactly. And so there's something called Hellman's time-space trade-off, which is for most functions you can add additional bits of information to reduce the computation time, which means that you can trade off more space stored on your side for less computation done later. What we're trying to do with the proof of space is adjust that trade-off curve from linear, here, to something a little more bumpy, and get out into this area where we can adjust time and space trade-offs. And so the core of the idea is to build a function where the quickest way to compute it, or rather the only quick way to compute it, is just to build a lookup table and fill up your hard drive with lookup tables. And so when we're talking about a proof of space, you have a lookup table for this function that's been combined with your public key. Anytime you want to compute a proof of space, you get a challenge, you look up your table, you see if you have a good proof there, and if you do, you submit it to the network. If you don't, you don't. The core idea here is that there's no way to compute this function faster than someone with a lookup table. And it's so much slower that you're not going to be able to compute in making a blockchain. It's much longer than the block time. So if you're computing on the fly, anyone who has a lookup table is going to beat you, so people will make lookup tables. And we'll fill up every available hard drive with lookup tables.
What's the value of all the space? Besides that I'm filling it.
What's the value of all the work done by proof of work? We're consuming a resource that can't be faked, essentially. You
So
can't,
instead of buying GPUs, I'm going to be buying hard drives.
or you're just going to be using hard drives you have lying around.
And what happens when space becomes so cheap that everyone's just buying more and more of it?
Well, the same thing that happened when ASICs became so prevalent that our hash rate, went hockey stick for a while. Difficulty adjusts on the network.
And is there any possibility of making the space useful for storage for other things?
Not if you wanted to run a consensus algorithm. If you don't want to run a consensus algorithm, go ahead and use it for other things.
No, I want to run the algorithm. I'm just wondering if I can, eventually this will be the cloud storage server that people use.
Probably, we're just storing random lookup tables on here. It's going to be functionally indistinguishable from random bytes. You're not going to be using, this is a cloud storage service. You're going to be consuming resources in a way that is provable, computationally.
So the contention is that that lookup table has to occupy your hard drive.
Yeah.
You can't fit anything else on there.
Not that you can't fit anything else on there.
Okay.
That in order to put additional things on there, you have to drop parts of the lookup table.
Yeah.
So you're dedicating the unused, for whatever you use on your hard drive, you're dedicating the unused that would normally just be unformatted or formatted space that you're not using for anything.
So at that point, the time competition becomes not who can compute to who can look up, but rather who can build the fastest lookup.
Lookup is done in linear time and only needs to, not lookup, creation of the
go-
lookup table is done at the beginning in linear time. Lookups are just something like 100-byte random read from your disk. So it's not going to be like very advantageous to build faster access, because what matters is not fast access. It's the strength of the proof that is there. Like in Bitcoin, where the strength of the proof of work is defined by the leading 0 bits of the hash, you have the same thing where the strength of the proof is defined by some characteristic of the proof. And so different proofs have varying quality, and if your proof is not quality, you won't bother submitting it to the network.
What
It's not
happens
about
if theoretically a single node has all of the tables
has all lookup tables.
Yeah.
You may not have a good proof in your lookup table. Like the quality of the proof is compared to the difficulty on in the block header, same way as in Bitcoin. And so if you don't have a good enough proof at the right spot in your lookup table, you just won't submit a block. You just don't get a block that time around. Maybe there's a disconnect here. You're not crawling over the whole lookup table to find something. You're looking at a specific index at each block, defined by a challenge number. What's that?
Effectively a key value.
Yeah. You're looking at a specific value each block based on a challenge which comes from the previous block.
Yeah. So I'm just kind of getting into like key values are cheap. If you can easily partition it, at that point you can separate the lookup, and it's really easy to actually have almost an infinitely sized database with this information.
Well, you can't have a database larger than your physical storage medium.
Well,
Can I just be plugged in
distributed.
Well, if it's distributed, then it's just going to be up to the sum of the disks it's distributed onto.
Yeah.
The size of the lookup table doesn't matter, it's what's at a specific index in that lookup table. You could put it across like a RAID array, you could put it on a single disk.
Okay.
It shouldn't matter. It's gigabytes or gigabytes. Yes.
So at the high level, the motivation is to create a more fair mining environment to save power.
Create a more fair mining environment, create something that its optimization has more positive externalities, create something that consumes electricity, hopefully. There's debate about whether you can ever consume fewer resources and still have a consensus algorithm with Nakamoto consensus. Anyways, yeah, make something that is hopefully more decentralized, better positive externalities, that kind of thing. Yes?
You use the phrase quality of proof. So
Right.
you either have that particular value at that index or not. So what's the quality of proof?
So I don't know exactly how Graham is defining quality. I expect it'll be something like leading 0 bits or some other quality of the value at that point in the key value store. So there's a special thing for us where proof of space has some weaknesses that we're not going to go into as a consensus algorithm. So combining it with proof of time helps fix those, and because you have 2 different proof processes, the difficulty is adjusted towards the product of those 2 proofs. And that means that as time progresses, proofs increase in effective quality, or the required quality for a successful proof of space goes down over time, is a better way of saying it.
Is proof of time another word for proof of work, or is it something different?
So, I'll get back to that in a second. I'm going to switch gears into the proof of time in a second.
Sorry.
Yes.
So do you pre-compute the key value pairs?
Yeah.
And if no one contains like the value for a particular key, then you have to actually perform the execution.
If you don't have a value for that key, you just won't do anything.
If no one.
It's not that there's a globally shared key value store. It's that your hard drive is using a key value store that is unique to you, and you are checking what's at specific indexes in your key value store. And so if there's something good at that index, provided that you have that index at all, you'll submit that as a proof to the network and build a block.
And how do you decide on like a particular partition of this lookup table that you want to store?
The idea here is that you can actually do this before you ever install anything on the drive. You calculate the lookup table across the entire drive, fill out the whole thing, and then you deallocate all the space and use raw disk reads from there. And so at that point, you just kind of add files like normally to your file system, and they just cover up lookup tables and delete it over time. And when you want to create a proof, you see if you still have that key value, and then what the value is, and then if you're good enough to build a block. Yes?
Would a reasonable analogy be everyone who's participating is pre-committing to a really large bingo card?
Yeah, bingo cards is a good way of thinking about it.
The next block is saying this, look there, and then you prove that the one you committed to earlier really is bingo. And if nobody has bingo in 5 minutes, the standard bumps down one or a new square.
Yeah, that's I think a really good way of looking at it is you have your bingo card that is your hard drive, and every time a block is produced, there's a challenge, and you see if you have a bingo or not, and if you think you do, you get up and wave it around, and over time, the quality of bingo required goes down kind of with time linearly. So yeah, I think bingo cards is a good way of looking at it. You create your bingo card once at the start, and then you wait until you have a bingo. Yes?
So assuming that somebody produces a block, they will include what value or proof they use to do that, and everybody across the network are seeing that, and they say, okay, for the previous challenge, this was the most valid proof of quality proof.
Right.
And then that becomes the head of the block.
Yeah. There's going to be some complications around reworks and stuff like that. Bram is going to talk about that more in the future, hopefully, because that's still up in the air a lot. All right, moving on to proofs of time. I've been trying to convince people to call them poets, proof of elapsed time. Essentially, this is actually really simple conceptually. All we need is a function that's faster to verify than it is to compute. And then you compute that function over and over as your proof of time, and you then can verify it over and over as the verification of the proof. So we use this, or what we're planning on using right now and haven't implemented yet is modular square roots. So find the square root of a number in a large, prime order field in a SegWit group, right? So you can compute this in, a set number of operations. It should take you log of n squared, where n is the size of the group. And you can verify it in log of n time. So there's a linear speed up for verification compared to computation. It's nice. The real trick here is that you can create a snark for the verification. And if you create a snark for the verification, then you can verify the proof in constant time rather than log of the order of the field. So we're creating this function that's faster to verify than to compute, and then we're making a nice little cryptographic trick to make the verification extremely quick, not the computation. So one of the really cool things here is you can then combine those snarks into a tree of efficiently computable snarks, and have one snark that verifies any number of computations of modular square roots. And so you can have one proof for any amount of elapsed time, essentially. And so the idea here is that this function is very simple to optimize. You expect to see people get to the fastest version very soon after release. And maybe it gets async for a slight speed up, but it's not a big deal if so. And from that point on, these proofs are generated at a constant set rate. And so you know that 10 computations of this modular square root takes a specific amount of real-world time, because it is impossible to speed it up any faster than that without having something like 10 to the 15th processors which is a lot of CPUs. So that means that you can use this proof and the one snark that you verify in constant time, regardless of the number of proofs, to prove that time has elapsed a certain amount since we started doing this. Does that make sense?
And so is everyone doing that?
So probably not.
In order to move on to the next lower level of proof of space?
You're more likely to see people, a few people running proof of time and sharing it with the network. And all of those people will move at about the same rate because they're all optimized. And it shouldn't be hard to find someone, like generating time proofs for you. It's hard to say exactly what the mechanics will be there because we're still in kind of design phase for this. All you need is one optimized implementation out on the network somewhere.
Are you implying that you're going to split a block reward between somebody with space and somebody with time?
I do not know.
Have you guys given thought to block rewards and time range?
Oh, yeah.
Block size and all that?
Yep. We've been thinking about it. Every block needs a proof of space and a proof of time in it in the current conceptualization, and this is where I'm going to get ahead of myself, and I should let Graham talk about it. Yes?
Could you have consensus with just proof of time?
I don't know. I don't think so. I wouldn't, but that's kind of an open question. That's really Dfinity's idea, sort of, is a stable random beacon as the root of consensus. Not something I've looked into much.
One last question. Dig deep.
Yeah.
Privacy implications? How private is the blockchain? Is it better than the
at least
state
as
of
private
art?
as Bitcoin.
That's not very private. If you're, I forget what you use the term, but if you're making everything into one, what did you say you're doing? When you're,
Aggregating.
what?
Aggregating.
Yes, when you're aggregating everything, you can't unaggregate it. Doesn't that kind of erase the trail?
So the pub keys are still committed to on-chain and still associated with the inputs, and then you commit to a script for the output. So the trail is still there. The signatures aren't the important part. Potentially you could use aggregate signatures to do non-interactive coin joins and things like that. So there might be some room for privacy there, or privacy gains there, but it's hard to say exactly what that'll look like.
That's it. Wow. Thank you, James.
Awesome. James, thank you so much. This was super awesome. This is probably one of the more engaged discussions we've had afterwards. Obviously, everyone is super interested in this. You guys, thank you for your amazing questions. We are going to be meeting in Brick House across the street, and stay tuned. We will have Graham come and speak because he owes us one. So I'll see you across the street.
Thank you.